For Lab 3, you'll be conducting 2 experiments. The first one will allow you to practice structural modeling, and the second experiment, Experiment 5, will allow you to practice some behavioral modeling. So Experiment 4 is about implementing the 4-bit ripple carry adder. And I went through a 3-bit ripple carry adder example in Lecture 5A, so that should give you a strong, almost giving away hint of how to go about implementing Experiment 4. So you want to begin Experiment 4 like you do with every experiment with a black box diagram. Yours will look something like this, but it should be more fully labeled than this, as fully labeled as the 3-bit ripple carry adder in Lecture 5A. And you'll go ahead and implement this function in iSim, in the simulator, and also on your board according to the inputs and outputs given right here. Now, what's great about doing the ripple carry adder is that you've already created the half adder and the full adder. You created the half adder in Experiment 0, and you created the full adder in both Experiment 1 and Experiment 2. So we're going to use the full adder from Experiment 2 because the one from Experiment 1 had 2 sum outputs and we only need 1 sum output. Okay, so how do you go about now reusing your code? So let me go ahead and start a new project here. I'm going to close this, close project. Let's do a new project. I'm going to add it to the directory I have here on the desktop for the 133 labs. Okay, and we're going to call this Experiment 4. Change this to Vhdl. Everything looks good. Oh, evaluation board, 3E starter board, Vhdl. Okay. Okay, so we've got our Experiment 4. We're going to create the top module for the ripple carry adder. And we already know that it's going to have 4-bit inputs A and B. And to get the 4 bits, we're going to do 3 down to 0. It's going to have a 4-bit output sum and a 1-bit output carry out, or whatever you want to call it. I'll just call it C out. Yeah. 1-bit output. Okay, so we have our ripple carry adder, and what you're going to do here is add all the structural modeling stuff in the architecture of the ripple carry adder in order to add in the components of the half adder and the full adder. But you also need to add those modules that you've already created to your project. So you can click on this plus arrow and add those other sources. Now, before you do that, what I would suggest doing is going into wherever you're keeping all your labs. So for example, I've got this CPU 133 labs folder on my desktop, and it has all my past experiments. And I can go into the Experiment 1 or 0 folder and pull out the half adder. Now, mind you, you're going to have a lot more code, a lot more files in here. I've just made this simple for you to be able to see that. So you pull out the halfadder.vhd file. So I'm going to copy it, Control-C, and put that into my Experiment 4 folder. And then I'm going to go ahead and go into Experiment 2 and copy the full adder file, the fulladder.vhd file. And you can find this file in your folder by clicking on the type and looking for VHD. So I'm going to copy that and put it in my Experiment 4 folder. So now I have the modules that I need for this ripple carry adder. I can go back to my project now, and now if I click on Add, I can add these 2 sources. And I can add as many as I want by holding down the Shift key while I'm clicking. So that's showing you I'm going to add both of these. And you'll see that they both appear in the hierarchy window. And I think I mentioned in my intro video, this little symbol right here is saying which one is the top module. So in this case, we know the ripple carry adder is the top module. It's got that little green dot there. And it should be, because this is what's the top, and inside that is the full adder and the half adder. Now, when you start adding components, I think the easiest way to add components is to go into your component itself and copy the entity, and in that copied entity, you can add it to your architecture and just change the name entity to component. So that way you make sure you have all the right names. And I'm going to copy in my half adder entity and make it a component. And then I can, in the begin the whole port mapping stuff using the names that I have in my components. Then what's really cool is after you do all the port mapping, what's going to happen is that these two files in the hierarchy window will actually appear beneath the ripple caryadder. So that way you know that they are subcomponents of the ripple caryadder. If they're not appearing over there, you've probably done something wrong. Okay, so that's the whole goal of experiment 4, is to practice structural modeling, practice implementing the ripple caryadder. And you'll have to use ISIM again. Now, you're going to be adding two 4-bit numbers, a 4-bit number plus a 4-bit number. You do have the option of going through all possible test cases, but you can sort of figure out that's going to be a lot of test cases. So when you're doing your ISIM and when you're doing your test cases on the development board, you want to think about test cases that will be representative of the circuit. Maybe you want to test end cases, you know, what happens if you get a carry or not a carry? What happens if you add zeros and zeros? What happens if if you get in between numbers and you get carries in between? So you want to create a representative sample of test cases that you feel would make you pretty confident that your circuit is working correctly. Okay, so now we're going to move on to the next experiment. The next experiment is a lot shorter than this one. Well, actually they're both pretty short, but the next experiment is the 4-bit comparator, and the whole goal of this is to have you practice using a process statement. So using behavioral modeling, using ifs and elses in your VHDL code. And what's really great about this is in a comparator, all you want to do is compare if A is greater than, less than, or equal to B. Now, if you read the chapter, which I hope you did, you would have noticed a whole explanation in chapter 11.4 of how to implement a comparator with gates. So it went through describing comparing a 2-bit number with a 2-bit number and seeing if they were equal, and showing you that in order to do that, you go through this truth table, you see that you get an XNOR gate, you get all this lovely Boolean equations, and you end up with, oh, we need 2 XNOR gates, one for the least significant bit and one for the most significant bit, and those both need to be ANDed together to see that it's equal. XNORs are really great because what they do is they check if 2 bits are equal. And then, okay, if we wanted to expand this to a 4-bit by 4-bit number, okay, we're going to add on more gates. And so this is just to determine if something is equal. So imagine if we had to do this gate level for both the less than, greater than, and equal to. It gets very complicated, and writing all this out, A3 XNOR B3 ANDed with A2 XNOR B2, using the concurrent signal assignments would get very long and tedious in VHDL. So that's where the power of the behavioral model comes in, where you can literally just create a process statement and inside that say if A is greater than B, guess what? You can use the greater than symbol in VHDL. Then equal is 0, greater than is 1, and less than is 0. Else, if A equals B, equals is 1, less than is 0, greater than is 0. So you see it becomes a really, really simple VHDL code by using this behavioral model. So if you recall, you would want to go to your polylearn, and at the very top of your polylearn there is the VHDL cheat sheet, and this will remind you of the construct of all these different VHDL constructs and the syntax for the process statement and how you would go about implementing that. So the whole goal of that is to practice using this process statement, realize the power of using this in VHDL. It saves you from all that gate level modeling, and have fun with it. So the write-up will include the write-up and the simulations for both the ripple carry and the comparator, and I only need to see the demo for the ripple carry adder on the board. Thanks.